Okay, perfect. So let's start with the, so yeah, let's record that. And we left it, so we left it here last time, all right? So we talked about the positional encoding stuff, did some testing code, and basically I think this is roughly understandable. Can I ask Ghostwriter to read the transcript? Can I copy, or can you, so can you please read the transcript file so you can refresh your memory of our past conversation? That's the problem. I kind of realize if you ask it like, can you, it tends to actually say that no. If I just say, please read. It's a text file in the REPL. You do, I know you do. Please access 27 and process its contents. I know you do. I know you do. You do, come on. It's a text transcript of our past chat history. It's our past chat history, bro. Do you remember talked about last time? Can you summarize our past conversation? Let's store it in a file. Exactly. It's funny because it actually gets it. It actually gets it. Yeah, so it gets it about positional encoding. We talk about positional encoding. So what is the seems like some connection issues because I can't even write now. So what is the best next step? That's my question. So what is the best next step? So positional encoding is one thing, right? And I roughly understand how that works. Now, no problem. So we talked about. So what is the best? What is the next thing to implement? So it's actually asking me to really instantiate this stuff, right? So let's do so in JS, please. What I call test code. Remember, we are doing this without any external libraries. So I almost think like I should actually so recovering, I think this kind of doing multi-session seems to be tricky. This seems to be, I think the best thing or the trick here would be to kind of craft kind of an initial prompt maybe that summarizes somehow everything. just so I kind of can spare those, like, well, I'm already 5 minutes in, right? So let's go back to, so go to the transcript and then take a look at the positional encoding. So this is what we talked about. So we talked about, let's reset combo a bit. So we talked about this last time. Oh, I can't, this, like, the character limit actually hampers me quite a lot. Let's go through. So we've done positional coding, multi-head self-attention. So tell me more about multi-head self-attention. So tell me more, and where does it fit into the architecture, to the transformers architecture. It's a core module. It's used to compute the attention scores for each word in the sequence with respect to all of the words and to aggregate the weighted sum of the values for all the positions. The multi-head model can be thought of as consisting of multiple heads or parallel attention mechanisms, which each of which can attend to a different part of the input sequence. The output from each head is concatenated and used as input to the next layer in the network. The multi-headed nature of self-attention allows the model to capture relationships between words and multiple levels of abstractions and to better handle long-range dependencies. Okay. In the transformer architecture, multi-head attention, self-attention is used both in the encoder and decoder layers. Exactly. So we have the encoder and decoder layers, and the encoder layer self-attention is used to compute the representation of each word in the input sequence, and the decoder layers context vectors for each position. Okay, so can you give me a link to sketch of the let's see if it gives me a valid link. No, not valid. Try again. With a transformer. Okay, so that is it's funny because if I managed, like, to realize if we actually managed to get that stuff implemented without having to go through all these, like, this is just going to be pretty insane actually. Test data set, data handling. Oh, there you go. This is the picture that I've seen. So you have the input, the output. So you have the input, there's multi-head attention, feed forward, blah 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 blah. And positional encoding is here. So we started fairly at the beginning, so it's actually not bad. So let's go to do the multi-head stuff. So there's the feed forward neural network in there. It's crazy because these all seem so simple, at least the kind of architecture, right? So positional encoding. Yeah, look at these. They're actually this sine and cosine stuff in here. Interesting. Okay. So let's go multi-head attention. Let's try to see what we can do in like 10-15 minutes, okay? So let's give it, so let's implement multi-head self-attention. So this seems to be, yeah, so let's implement multi-head self-attention without any external libraries. So what do we have here? Cool, a lot of code. I like that. So I'm not so sure if that's all of it, because sometimes it truncates the thing, but it does a return statement. So, oh, wait a second. Yeah, Python. Why did I ask in JavaScript? I'm sorry, guys. I was doing the other. I was doing the other project with the simulator, and I think because it was JavaScript and it tend to give me stuff in Python instead, like that just got into my, it just got basically engraved in my head, in my brain. So we've got a function here, that's a lot to unpack. So let's ask it to explain, or let's first read that ourselves a bit. So there's a function called dot product attention that probably something about dot product multiplying matrices and whatnot, multi-head attention. So you initialize these, this D model thing, and then the number of heads. So that's cool. And then here, I guess what it's doing is, so it's initializing the sort of the, this is a bunch of matrices, right? So let's see. But it seems like it's kind of doing an initial random initialization. Yeah. And it's gonna, it seems like it's a similar concept like with positional encoding. So this is all seems to be all pre-processing, right? Before it actually goes through this neural network. Because I don't know, what is it that makes the prediction? At what point? Why the inputs and outputs, the output embedding? I'm not so sure I understand why there's this kind of like two-lane thing. Should probably save image or copy image. Can I paste the image on the repository directly? Can I paste it? No, but I'll just probably open image in a new tab. Let me see. I'll just move away because I there might be some sensitive data in that I don't want you guys to see. Architecture .png, and then we just go ahead and upload that in here. So at least we have these as well in the repo, so we can take a look at that image. We can actually have it here. Oh no. I wanted to have this separately. Although maybe it makes sense to have it all in one thing, because then you have more screen space for everything, and I don't really need to have Ghostwriter separately. Just write stuff here, copy here. So okay, cool. We have the architecture stuff here now. So we're doing the dot product. Okay, so this seems like the same concept, right? So you have position code, you have the multi-head attention as a class here. So essentially what this is doing is initialize it randomly. I don't know what the split heads is doing, and then this kind of call thing is what it's doing some multiplications. It's doing the head, something with the heads. I don't know what split heads does. It's calculating some attention weights by calling this and then transposing, reshaping. I guess this is all just mathy stuff, so that you can then multiply things the right way. But let's definitely try to understand that, and then you kind of have the output, and then you return the output and the attention weights. So what is init doing? Ghostwriter. So what is init doing for the multi-head stuff? As a constructor, it initializes the variables, right? So we have the D model, this dimensionality of the model, the size of each vector in the input, output and internal representation of the multi-head attention mechanism. I guess it's the same. I don't know if it's the same that you're using for for the positional encoding. I guess it's the same. Num heads, the number of attention heads to use. This determines how many times the input vectors will be separated into different parts, and each part will be processed by a different attention head. Okay, it's just a hyperparameter, I guess, or parameter. Depth. This is the depth of each attention head. The size of the vectors resulting from processing the input with each head. These are the weight so these are weight matrices that will be learned during training. Okay, cool. So this is where the learnings go. They're initialized at random. At the time of instantiation. Okay, so yeah, so that's why they're initialized randomly. What does split heads do? So split heads do probably, so what does split heads do? It splits the input tensor into num heads. I guess where so this is basically the input tensor is where the input is encoded, including the positional encoding stuff, right? So this is, I think, just stacked, right, like after each other, and then essentially what's happening is this is then split into multiple heads, or into multiple kind of batches. It reshapes the input tensor because it adds a dimension, it adds a depth to it. The transposing happens so that the num heads dimension becomes the first axis. Okay, so the idea is that you're parallelizing, so you can parallelize this stuff. Yeah, we'll have to dig into this a bit more, and then it returns a tensor which is of this shape. Each slice along the num heads axis represents a different part of the input that can be processed by a different attention head. Okay. So that just prepares the input so they can be processed in parallel. We'll dig into these, okay, next time, because I'm not gonna have time today, but at least we've done multi-head attention. Then and what does the actual call do? So the call method, okay, so that is, okay, interesting. So it performs a single forward pass through the multi-head attention mechanism given the query, key, and value vectors as input. The query, key, and value vectors are first passed through the linear layers, respectively, to project them to higher dimensional spaces. The projected query, key, and value are then split into the num heads. It's going to the previous answer. The split query and the vertex are then passed to the top product attention method to perform the actual attention calculations. The resulting attention scores are used to weight the corresponding value tensors using a matrix multiplication, and the resulting weighted values are concatenated through a linear layer dense to produce the final output. Okay, that's where the actual stuff happens. This is okay. So we have to actually break this down because this is where we need to make sure to understand each step. But essentially, this performs a single forward pass through the multi-head attention mechanism. It takes the input vector. So it takes the input, and essentially, well, it's what it's doing here, right? So it just seems too simple, as in like, okay, no, it takes Q, so Q, K, and V. So this is query, but I'm not sure I understand these. So this definitely you need to ask what is the query and the key. So what are the query? In the context of sequence-to-sequence tasks, there are where the sequence is represented as a sequence of vectors. The query and key vectors serve as a way to capture the importance of each element of the sequence with respect to each other. So the query vector represents the current element of the sequence that we're trying to compute and attention for, and the key vectors represent all the other elements. Okay, of the sentence comparing to the query 2. Machine translation, the query vector might be the current word being translated, and the key vector might be all the words in the source sentence. Okay. The dot product of each query vector with all the key vectors gives you the attention scores. Okay, why the dot product? Is it because of the perpendicularity thing or the orthogonality thing? As in, like, indicating how much each key vector should contribute to the output for the given query vector. Huh. So this is all essentially calculating more information, as in like it's calculating for every single token or every single part of the input how much relevant the other elements in the input are for this one, right? I guess this might be something related to, like, let's say if the word is tree and then there's like an adjective before, like green tree, right? I guess the green token or word is gonna have a higher weight, like more attention for the relevancy of like how relevant. So the green is way more relevant for tree than if, let's say, if a sentence like in today in the morning I saw a green tree, right? I guess morning or today are less relevant for the word tree than green. Green is way more relevant. I think that is kind of what's happening here. So it's building that. It's pretty cool. So it's actually it's building that kind of attention as like how much relevant certain words are for other words, right? And that's all stored like in this matrix. I'm just not sure what I need to dig into. That we're definitely going to spend some days in this part, because that's the first one is easy, but this is going to be this is I want to make sure that we dissect this carefully. Why does the dot product give you good results, right? So what is the dot? Attention scores. It's efficient. It scales well. It captures that's my point. It captures similarity. That's the point, because we're expressing tokens. Okay, yeah, but that's similarity, as in the dot product measures the cosine similarity between the query and the key vectors, which is a measure of how similar they are in direction. It can be an effective way to capture relevance, because the dot product essentially, it's kind of like, I think if two vectors are orthogonal, this means they are absolutely not similar at all. It's like it gives you a 0, right? So there's like a good, I think it's a good mechanism to calculate these, but I'm not so sure if that direction, how you make sure that that directional similarity has anything to do with attention. Like the word green and tree, they will, you know what I mean? Like they I'm not so sure if they're vector representation and then the corresponding dot product, whether that makes sense at all, right? Because the vector representation of green or tree will actually encode the token itself, but it will also encode then it will also have positional encoding, because it's what comes before. First you do the positional encoding, and then you go to the multi-head attention mechanism. So Twitter, this one goes right there. This is where I'm not so sure of like why it works, right? Why is it that you want similarity, or why is it that we translate similarity with attention? So by similarity we mean measuring how closely related two words are in the context of a sentence. Often used mechanisms. Yeah, exactly. Sure. In machine translation, attention mechanisms are used to help the code produce the most relevant output for to the current output word. The attention mechanism can highlight the most relevant parts of the input sentence for translation. Yeah, I don't think that answers my question. By similarity, we mean measuring how closely related two words are in the context of a sentence or a sequence. so you're measuring how closely related they are, right? But in a way, these seems to just be an actual physical similarity, as in like the word similarity and then the position. So far, as far as that's why I kind of had the feeling. I'm not so sure if that's. Oh, okay, that's not true, right? Because the positional encoding has multiple dimensions. So in theory, the positional encoding encodes more than just position. I guess it's a misleading name. The positional encoding encodes other stuff. That's why you have multiple dimensions. It can features, right? It encodes multiple features of words. Yeah, so adjectives and stuff like this. Yeah. This is where where the complicated part comes in. That's why you do positional encoding, to kind of encode those features into the words, to the tokens, in such a way so that then this attention mechanism can really do its magic and see, okay, so what words are more relevant for any given word in your input, right? I'm not so sure what is this going to lead to though. So because then it's just this feed forward box, which I don't know what it does. But I think that's all fine, and I think I'm not gonna. I don't want to keep transcripts. Let's try without transcripts. Delete. We're not playing with transcripts, so we're going end to end with these. So we're gonna have to live with the model's limitations. But I mean, okay, I didn't make it to test that, but I think I understand what it's roughly doing. But I still want to dissect that a bit more. So in the next session, we'll be testing the multi-head attention stuff. And actually, maybe what we should do for the next session is actually take a look at a smaller example of these, like an actual sentence, and then play with an actual input. Let's play with an actual input. Let's try to play with an actual input and then analyze how these encodings and how all this kind of stuff works. That's what we're going to do next. So not testing code, but play sentence and analyze. Encodings, positional, multi-head. Because essentially what's happening here is the rest is just some kind of, I guess, normalization stuff, and then there's these things here, and then we need to understand how the rest works. But it doesn't look like it's crazy. It's not a crazy mechanism. It's like encode the stuff, calculate attention and relevancy, and then do something. So really at the core of it, there's really it's really some sort of neural network, and that's it, right? Just with this kind of special encoding. Well, maybe that's the reason why the whole original paper for this was just all you need is attention is all you need, right? As in, you don't need any other more convoluted ways to design such things. Anyway, see you in the next session.